All right, as promised, I'm going to work out the problems here on the nuclear chemistry worksheet, so you'll have solutions to this, so you can check yourself. So first off, we've got this alpha decay of radon 198 that we're going to do. So let's write radon. That's Rn 198. You can look at the periodic table to get the atomic number or the number of protons of the radon. And if it undergoes alpha decay, you have to know that alpha particles are a 4,2-He. So you bring that in. That's going to be one of the products. And the other product we can get by subtraction. So initially there are 86 protons minus 2 would give us 84. Look at the periodic table, and element number 84 would be polonium. So PO. And then 198 minus 4 would give us 194. Okay, notice that there's plus sign here. 4 plus 194 equals 198. 2 plus 84 equals 86. And we use the periodic table to take us from the atomic number to the symbol of polonium there. All right, next up we got a beta decay of uranium-237. Mass number up top. Look at the periodic table. 92 is the atomic number. You have to remember that a beta particle is a 0 minus 1 E. That's an electron. And then let's work it out so the numbers work out. So 93 plus negative 1 equals 92. And then we can look at the periodic table and find element 93. That's neptunium, Np. And 0 plus 237 would give us 237. And I'm saying 0 plus 237 gives us 237. So this was the unknown as I was describing it there. Just check your numbers, make sure that if you add these together, you get that, and it checks out. So we're good to go. Positron emission. So let's produce a positron. Remember, a positron is the antimatter equivalent of an electron. So it's a 0 plus 1 E. And we're doing that from silicon 26. If you look on the periodic table, silicon has an atomic number of 14. All right. And let's see. So it would have to be 13, 26. So 26 plus 0 would make 26. 13 plus 1 would make 14. Again, look at the periodic table. 13 would be aluminum. And everything checks out. So we're good to go. All right, electron capture. The electron capture is going to be the same particle as a beta particle, except if it's being captured, it will be on the left side of the arrow, indicating that it's being grabbed by this sodium 22 nucleus. Look on the periodic table, and you'll see that sodium has an atomic number of 11. Let's put an electron over here because it said electron capture. And then, let's see, 11 minus 1 is, there's a plus sign between 11 minus 1 will give us 10. 22 plus 0 would give us 22. And the particle that would be produced there, let's see, number 10 is neon. All right. Let's see. All right, number 5, number 6, number 7, you can probably look up on your own or in your notes. Let's see, number 8, the way you can tell the difference between chemical and nuclear. So generally speaking, if the nucleus changes, it's a nuclear reaction. And if the nucleus doesn't change, then it's a chemical reaction. All right, tells us this about carbon-14, that it has a half-life of 5,730 years. It asks us how much is left after 1, 2, and then 3 half-lives. So after the first half-life, half of the sample would be remaining, so that would be 5.0 milligrams. And then after 2 half-lives, half of that half would be remaining, so then it would be 2.5 milligrams remaining. And then after 3 half-lives, half of the 2.5, so 1.25 milligrams would remain. All right, this one says that there were 25 milligrams after 5 half-lives. How much was present before it began to decay? So we're going to work backwards here. If you have 25 milligrams after 5 half-lives, we're going to basically times it by 2, a total of 5 half-lives. So we'll do this 5 times. You don't have to show your work exactly like I'm doing, but so 1, 2, 3, 4, 5 half-lives are going to go by. So on the previous half-life, it would have been 50, then 100, then 200, then 400, and then 800. So we would have started with 800 milligrams. All right, and you should also be able to look up the answer to number 11 in your notes or online if you would prefer. All right, folks, have a great evening, and thank you for checking this out.